we have Matt Shadwell, who's one of Rod's students, who is doing the all-important business of making these domes airtight. Matt, welcome to the stage.
So, Penny, I have to say thank you for mentioning that we need engineers. I'll pay you later. So I'm going to talk about our lunar environment simulator. So we've been hearing about some things like spacesuits, vehicles, structures, but how do we know that when we're designing, building, testing these on Earth, that they're going to work when we actually take them to the Moon or to Mars? And that's why you need a simulated environment. So there's lots of things that we might want to simulate for that are on the surface of the Moon. We've heard about some of the dust. There's meteorites that are coming in, there's radiation from space, there's the solar loading, there's reduced gravity. So if anyone knows how to reduce the gravity, let me know. But the challenge that I'm going to talk about today is the fact that there's very little atmosphere on the Moon. So to be able to simulate being on the surface of the Moon, we need to remove all of the Earth's atmosphere from an enclosed volume, which is our simulation environment. You might say, well, you're basically trying to create nothing. What's so hard about making nothing? Atmospheric pressure is basically the reason why it's really hard to create nothing, because as we suck everything out of something, we try and create a vacuum, the atmosphere tries to rush back in. Atmospheric pressure is something that you might not think of very much, but it's all around us all the time. It's analogous to if you go down to the bottom of the ocean, the pressure is very great. If I told you put on your swimmers and dive to the bottom of the ocean, you'd probably say no way, because I'm going to be crushed because all of that water is pushing down on top of me. And it's the same thing with all the air in the atmosphere pushing down on us. In fact, it's pushing down with a force which is equivalent to about 10 tons per square metre. So while the pressure of the air around us is only about half of that you put in your car tyre, when you add that up over a large surface, it ends up being about 10 tons per square metre, and that's quite a lot for a building to hold up. You might say, there's a square metre, on my surface. Why am I not getting smashed by 10 tons? The thing is that I am, but it's coming from all around, so it all balances out. And likewise, there's a lot of pressure pushing down on buildings. There's a lot of pressure pushing back out from the inside. The problem is when we try and suck all the air out of our building to simulate being on the Moon, there's then no pressure pushing out, a lot of pressure pushing in, the building wants to collapse. So we need to come up with a really good design. And that's where the dome comes in. Hooray! So, hooray! Domes and arches have been used for hundreds, if not thousands of years, because they're very strong structures. They're able to very efficiently transfer a lot of compressive force down through the ground and thereby keep themselves standing up. So you can see behind me here a 3D model of the dome that we're talking about. This is the first one that Boswell Technologies is going to have built. It's a 3-metre diameter dome, and it's made out of reinforced concrete. Not the most exotic material, but very strong under a compressive load and reasonably cheap and easy to work with. And if the whole thing fails, as you can see, at least we can sell it to the ACT government as a new bus shelter. So, concrete is strong, domes and arches are strong, but why take my word for it? So what we've done is done some simulations. We create a 3D model of the dome in some engineering software, chop it up into lots of little pieces like the mesh you can see behind you, apply the load of atmospheric pressure to all of those little elements. It's called finite element analysis, where you add up all the little forces acting on the little bits, and as a whole you can work out what the structure is going to do when it's under that load. So what does it do? Behind me you can see a plot, and it's coloured by the amount of stress that the concrete is experiencing when you've sucked all the air out from the inside. the bulk of it looks pretty smooth, but then you can see some different colours around the door opening and the window openings. And that's because around those discontinuities, that's where the stress concentrates. And that's why we have to have relatively small openings, and they have to be relatively smooth shapes. So if you have a sharp corner, the stress is really going to concentrate there, and it's probably going to crack the structure. Now, who wants to be inside that when it's crushed like that? That's an exaggerated plot so that we can see where the most deformation is going to occur. In reality, it's only going to deform by less than 1 millimetre, which is less than, say, the thermal expansion as it heats up during the day in the sun and gets cold overnight. So we know that the amount of stress that the concrete is experiencing is within its limits, and we know that it's only going to deform when we suck the air out by about 1 millimetre due to the atmosphere pushing in onto it. So we're pretty happy with that. So what else do we need? We need some clear perspex windows and a door hatch so that people can get in and out, and a bit of gold cladding like you can see there to make it look a bit fancy and space age. As I said, that's the 3 metre diameter dome, which is the first one that's going to be built, and all going well, not collapsing on anyone. As Rod mentioned, then maybe a 12 metre dome, allowing some bigger and more exciting things to be put inside to simulate how they're going to go on the moon or on Mars. That's it.